I am Dr. K.C. Jain, and today we are going to discuss the electrodynamics. This electrodynamics is basically involves the equations of electrostatics and magnetism. So this electromagnetism covers both electricity and magnetism. Electromagnetic interactions basically involve the charge particle, and charge particle here is electron. If charge is in rest, then electrostatic interactions occurs, and these interactions are governed by mainly the Coulomb's law, Gauss's law, or we can say in conclusion electric field. Charge particle, if moves in an electric field, the field exerts a force and that can do work, and work can be expressed in terms of electric potential energy, and this gives electric potential. Again, if charge particle moves with constant velocity, magnetic field is produced, and Biot-Savart's law and Ampere's law can be used or can be applied for the moving charge, and moving charge is also a source of magnetic field. Now, if magnetic flux changes, an EMF and current are induced, and electromagnetic inductions can be governed by Faraday's law. It says that a time-varying magnetic field can act as a source of electric field. From the concept of displacement current, time-varying electric field can act as a source of magnetic field. These all results are set in Maxwell's equation, as already we know, and predict the electromagnetic waves which travels with speed of light, and the theory is known as Maxwell's electromagnetic theory. Now we will discuss about some points before discussing exactly the electrodynamics. So first of all, field. So what we can say, that physical quantity can be expressed as a continuous function of the position of a point in a given region. It's called a point function, and the region in which it specifies the physical quantity is known as field. The field may be of two types, the scalar field and vector field. If the quantity is scalar, then it will be expressed in terms of a scalar field, and if it is vector, then the quantity will be vector, then vector field will be used. Now next, gradient of a scalar function. So we can have a gradient of a scalar function, and we can express it as grade phi or del phi, that is equal to as a del operator, and it will be operate on a phi scalar function. So we can write del operator I del upon del x plus j del upon del y plus k del upon del z phi, or this can be written as del phi upon del xi, del phi upon del yj plus del phi upon del z k. And del phi, as from the above, it is clear that it is a vector quantity and phi is a scalar quantity. So we can say that if we want to calculate a gradient of a scalar function, then always we will get a vector quantity, and if suppose phi is equal to constant, then del phi will be equal to 0. The famous formula that already we know, that E is equal to minus grade V, or E is equal to minus del V. This gradient is basically maximum increase of the function phi we can calculate. Divergence is del dot phi, that it is del dot f, that it is a scalar product between of two vector quantities, and that we can write I del upon del x plus j del upon del y plus k del upon del z, that is del operator, and we can make a dot that shows the scalar product, and a function we can write fxi plus fij plus fzk, and del dot f that we can also write as divergence f, and that is equal to del fx upon x, del fi upon del y plus del fz upon z. And divergence of a vector is scalar. This divergence basically shows that how much the vector f spreads out. That three diagrams are there. If this A diagram says, then it is a large divergence, and the second zero divergence, and the third positive divergence. If divergence is positive, then it is a source, and in case of it is negative divergence, then we can call it as a sink. Now the curl of a vector. Curl is the cross product of del operator and f function, so del cross f, and it obviously it will be a vector quantity, and this curl shows that how much the vector is turns around the point or curled around the point. So we can calculate the cross product between the del operator and f, that we can write I del upon del x plus j del upon del y plus k del upon del z, cross product fxi plus fij plus fzk, and we can have the idea for the cross product. Now the line integral. Line integral, that is from a to b, if we integrate a function f dot dl, then it will be, we can write f cos theta dl at its a cross dot product. Surface integral f dot ds, double integral surface integral, we can write like this, double integral there, and we can write f cos theta ds, where ds is the surface integral value. Volume integral, that is triple integral f dot dv and f cos theta dv, we can write. Integral theorem, these are the important theorems. That is divergence theorem. This divergence theorem, we can convert the volume integral into surface integral. That if we have a volume integral, then it can be converted, or we can write as surface integral, that del dot a dv is equals to a dot ds. Similarly, the Stokes theorem, that del cross a, that is curl of a vector, del cross a ds, can be written as, in terms of line integral, that is a dot dl. So these are the some points, or we can say the idea and the theorems that we will use in the next 2-3 lectures: the curl, divergence, gradient, line integral, surface integral, volume integral, divergence theorem, and Stokes theorem. In this chapter, mainly our aim is to write the equations of electrostatics and magnetism into curl, divergence, and gradient form. Earlier, we have the equations that we have in electrostatic field and magnetic field are, we can say, in direct formula, but here we will write these formula either in integral form or in differential form. Thank you.